Alright, so this is going to be the solution to the 22nd problem of the grind 75. This is diameter of a binary tree. And as you can see, I have my camera on now. I thought it would be a good idea to sort of simulate what the actual interview would be like. And it definitely already feels like I'm talking to someone now as opposed to talking to no one. So let's read through the problem description. Um, Given the root of a binary tree, we want to return the length of the diameter of the tree. And what the diameter is the longest path between any two nodes in this tree. So I'm going to look at this first example, but we're going to actually switch over to Paint really quick. And basically, the solution that I came up with originally was to, let me switch over, was to get the height of the root. You want to get the height of the left side and the height of the right side, because that's kind of like one path right there. And we would add those up. And I thought that that would give us the largest diameter, but it's definitely possible that we get, something like this, and we find out that if we were to just take the height of the left subtree and the right subtree, this would be 1 plus 1, 2, 3, 4, which would give us 5. But this would actually be the longest path. We go 1, 2, 3, 4, 5, 6 right here. So in that case, basically we would just apply the same algorithm. We would just do it on every node. But the thing is, if we have to calculate the height of a tree first from the root and then from each node, the time complexity becomes O of n squared. Because for every node, we have to touch every other node, and while that value declines over time, the over basically what it is in amortized time is O of n squared. So the faster approach would be to figure out the diameter as we're climbing up the tree. So once we've gotten to the bottom, then we want to start to figure out the height of each node and then see if the diameter that it yields is greater than a diameter we've already found. So basically what that looks like is once we get to a root node, or a leaf node, I guess. Once we get to a leaf node, we'll see that its children are null, so they contribute nothing to the height of this tree, but that will allow us to return back up the recursive stack. This time we'll add 1 to that recursive call. So we're adding 1 going this way, and then also, of course, adding 1 going that way. And so we will have a height of 1 on the left side and a height of 1 on the right side. And we can now reassign the diameter to the maximum of whatever our current value is for the diameter, because right now it's 0 if we're going down the side. So we can reassign it to the current, or we can reassign it to the addition of our heights of the left and right subtree. So in this case, it would become 2. So let's go over the implementation of it really quick. I'm going to switch over to the LeetCode window. Let me see. Okay, let's see. Okay, so because we're keeping track of diameter globally, we are not going to want to confine it to this one function here. So I'm going to define it out here as public int diameter, which I might just be able to do as int diameter. I'm going to keep it public int diameter. We're going to initialize that to 0. And because this is a depth first search, we're going to put that functionality into its own function. So we're going to just call the function we're going to define called DFS on root, and then we're going to return diameter. Okay, and so let's actually flesh out DFS. So DFS is going to return an integer, and let me see. Yeah, it's going to return an integer, and it's going to take in a tree node we can call root for now. And basically, what it's going to do is we're going to start off by just implementing the base case. So if our root is equal to null, then we know that our height is 0, so we're just going to return 0. Otherwise, we're going to make recursive calls going down the left and going down the right. So we're going to say int left is equal to DFS on root.left. Similarly, int right is equal to DFS on root right. And once we calculate that, there's the two things that we want to keep track of. So the recursive calls are going to be adding to our height, right? So what we want to return inside of this function is the height, right? The highest, the greatest height that we can from that we're getting from our children. So we're going to do math.max of left and right. So this will essentially return, the height. So if we're looking at this example right here, and we want to return up this stack, we have the maximum height of 1 here, and then we're going to add 1, and that's going to give us 2. But we also want to have some sort of diameter, which we have up here, but we want to update it if we found a diameter that's greater. And what exactly we're looking for is basically just whichever is greater, left and right, or the current diameter. Okay, and I believe this should work. Let me see if we just gonna run to make sure we don't have any missing semicolons or syntactical issues. Okay, so that works. Turn diameter. Let's hit submit and see if we've gotten somewhere. Yeah. Okay. So that has been the solution to the diameter of a binary tree. I think this is the 22nd problem in the grind 75. And yeah, we're going to conclude the video there.